Okay, so this is 347. Um, we are actually working with hanging a flower pot here. I'm not sure why anybody would go through this type of work to calculate all the forces just for hanging a flower pot, but that's what the problem is. All right, so what we're looking to find is the force in each cable needed to support the 20 kilogram flower pot. So this flower pot at the bottom is 20 kilograms. Let's convert that just to a weight or a force. 20 times 9.81, 20 kilograms times 9.81 meters per second squared. And what we get is 196.2 newtons. All right, so that's the weight of the flower pot here. And I've drawn the vectors here on the diagram, and what I've labeled each of the cables as in tension, TAB, so that's the cable from A to B, TAD from A to D, and also tension from A to C. Okay. All right, so what we're looking to find here is TAB, TAD, and lastly TAC. Right, and we know that this is an equilibrium, so we can start our analysis. And what we're going to do is sum all the forces in all the x, y, and z directions. And that should give us three separate equations, which then will give us, and we have three unknowns, that should be enough to solve this problem here. All right, so let's start by summing the forces in the x direction and setting those equal to 0 because we know it's an equilibrium. So x direction, let's take a look here. So this is the x direction here. All right. So to do this problem, I think it would be helpful to find the length of each of these cables. I think that's important to know. So let's do the position vectors, all right, the position vectors or the lengths of the vectors. Let's do from A to C first, okay? And the length of that here, the length of the position vector. So in the x direction, for A to C, we have 2 in the x direction. We have in the y direction, it's right, let's see, y is -4 here, so plus -4 squared. Oh, messed that up. Okay, so the 2 is correct because we're going from A to C. So that's +2 in the x direction. In the y direction, from A to C, we're actually moving in the positive y direction from A to C. So that is 4 meters. And then lastly, in the z direction from A to C, it's at the same z height, so that is 0, so 0 squared. And then we take the square root of that. So from A to C, that looks like the square root of 20. That's the length of A to the cable A to C. All right, from A to D, I would guess, since this looks kind of symmetric, that comes out to be the same thing. So from A to D, we're moving in the x direction this time. It's -2 squared. In the y direction, we're moving in the positive y direction as we move from A to D, and that's 4, so plus 4 squared. And then in the z, again, we have 0. All right, take the square root of that, and then we have the total length of cable AD is the square root of 20. And then lastly, our cable from A to B. So A to B here. So A to B. In the X direction, we don't have anything. It's straight in line with the X direction, so that's 0. As we move from A to B in the Y direction, right, in the Y direction, we're actually moving backwards in the negative direction as we go from A to B. So that's -3 squared. And then in the Z direction, we're moving positive up as we travel from A to B, and that is 6 squared. So we take the square root of that, and that comes out to be the square root of 45. Okay, so let's get back to it. All right. So we're summing the forces in the X direction. So we see that cable AB, right, the forces can only act in line with the cable here. So AB is going to have no influence on the X direction here. So only the cables that move in the X direction we can see by the components here. So only TAC and TAD will have influence in some of the forces in the X direction. So we have TAC, and the direction it moves in the X direction from A to C is +2. So the component of TAC in the X direction is +2 divided by the total length of cable AC, which is square root of 20. Okay. Then we need to take into account cable TAD, the tension in cable AD here. And in the X direction, we see that's moving from A to D. That's in the negative X direction, so that's -2 over the total length of cable AD, which is 20, and that is 0. Okay. So we have two unknowns in this equation, and we only have one equation here. We can't solve this for individual unknowns here, but what we can see if we move this to the other side, we can see that TAC, the tension in cable AC, is going to be equal to the tension in cable AD. Right? So now we need to sum the forces in the Y direction. And maybe I can move this diagram down so we can see what we're doing. All right, took me a while, but we got it. All right. So to sum the forces in the Y direction, right, all three cables are going to have some sort of influence on the sum of the forces in the Y direction. So let's start out with TAC. TAC, and the components in the Y direction here for TAC, it moves +4 from A to C, and the total length of cable AC is square root of 20. All right, and TAD plus TAD, and as we move from A to D in the Y direction, that's also a +4 divided by the total length, which is also square root of 20. And then lastly, we have the Z, or I'm sorry, the cable AB, so TAB, and that moves in the negative direction as we travel from A to B. And the y direction there is -3 divided by the total length, which is square root of 45. And that is all equal to 0. Okay. So we could start subbing stuff in, but let's hold off on that. So that's our second equation. And then lastly, let's do the sum of the forces in the z direction. Okay. So TAC and TAD do not move as you move from their origin to where they're connected to the plates here. Do not move in the z direction. So those will have no influence on the z direction. So TAB is the only one we have here, TAB, and in the z direction we have a +6 as we move from A to B, divided by the total length, which is square root of 45. But the pot is also hanging in the z direction, so we need to take that into account there. And that is downwards at 196.2 newtons. So with that being said, we can set that equal to 0. And this equation is directly solvable. We get TAB is equal to 219.358 newtons, right? So that's one of our answers. We need to circle that. Now we need to take this answer and sub it back into this equation in the y. So we take this and we move it into our location here. And we know AC, TAC and TAD are equal, so we could just change one of those to the other. So for example, we would just scrap this and put in TAC right here as well. And then we can solve for TAC. Which is 54.8 newtons. Okay, and we know TAC is equal to TAD from our x equation right here. So we can just say that that's also equal to TAD. So that is our other answer. And let's be careful about our significant figures here. I've listed too many here, so I'm just going to erase. So this would be 3 significant figures. This would round to 219 newtons here. Okay, so that is problem 347.